Assalamu alaikum. How are you, my dear students? Hope you will be fine and okay. Today is our lecture number 6, and it is about Hukla in young modulus. So let us start with the name of Allah Almighty. Bismillah Rahman Rahim. Let us start our topic with the Hukla. That what is Hukla? Robert Hooke was a French mathematician and physicist, and he first experimentally determined the relation between stress and strain. In the previous lecture, I told you that the deformation or the change in shape or size, that is the length, volume, or area of an object, is all associated with the stress. They all depends upon the stress, right? So to explain or to find a mathematical relationship, Hooke worked on it, and according to the Hooke law, this law states that the Hooke law states that the strain produced in the body, the strain or the deformation, the strain produced in the body, the strain produced in the body is directly proportional, is directly proportional, is directly proportional to the stress applied on the body, to the stress applied, to the stress applied on the body, provided that provided that the elastic limit of the material does not exceed, provided that the elastic limit does not exceed, or in a very simple words, we can say with an elastic limit, stress strain is directly proportional to the stress applied on the object. What? To the stress applied on what? To the stress applied on the object. So mathematically, we can write it like this, that the stress is what? That the strain produced in the body, the strain produced in the body is directly proportional to stress, or we can write that stress, because strain can also cause stress, because stress can also cause strain, so stress is directly proportional to strain. Or we can write that the ratio of stress, that is stress is equal to what? Constant into what? Into strain. Or we can write that the constant is equal to stress divided by what? Divided by strain. So this is what? This is the Hooke law. Now, before explaining to you this constant, I want to explain to you that what is this constant. This constant is different in different situation, that whether the stress is longitudinal or elongation, that is it is in the length of an object, or it is associated with the area, or if is it change or deformation in the volume. So if it is deformation in the length, then it will be of some different kind. If it is in the area, or whether if it is in the volume, so for different it is different. This is why here it is only written that constant is equal to what? Stress by strain. Now let us explain this both graphically as well as from the experiment. See here, look, let me just bring these two together so that let us see the experimental arrangement for the demonstration of the Hooke law. The we just want to find out the extension, right? So you see that look, there is a spring, a slinky spring, as you see. The spring is now in its mean position, means that it is at the point of no disturbance. There is no force acting on it, and I will label the length of the spring as this one. This is the length of the spring, as you see. Okay, now it is before any weight attached to it, it reads as 0 centimeter on the scale. The ruler, you see the meter rod is placed parallel to it. Now look, if we see here, look, here in this case, we attached a weight of 5 Newton to the spring which is supported through a hook here. Now let us see that for the 5 Newton force, there is what? There is an extension in the spring, you see. Look, for the 5 Newton force, the extension in the spring is what? The extension in the spring is 11 Newton, like this. So you see, look, right in the beginning, for the first 1 Newton force, look, for the 1 Newton force, if there is 1 Newton force acting on this, that is hanging from the spring, then the extension caused by it is how much? 2 centimeter, as you see here. Now for the, when you increase the load from 1 Newton to 2 Newton, then let us see what is happening. For 2 Newton force, the spring further elongates by how much? To 4 centimeter, to 4 centimeters. So what is the change in the length, as you see? Look, for 1 Newton force, there is increase of what? There is increase of 2 centimeter. So see here, look, when you increase the force to 3 Newton, then what happens? The extension reaches to what? And the extension reaches to 6 centimeter, as you see on the scale. Look, for 6 Newton, it will be somewhere here. Okay, and then further for what? For the load of what? For the load of 4 Newton, the extension is what? The extension is 8 Newton. So when you increase the load, so the extension went on the scale to 8 centimeter. It goes to, sorry, to the 8 centimeter, right? And this the same way for this, for this, for this, for this, and for the 6 Newton also. And this is your assignment. You have to tell me that what it will be for the 6 Newton. Okay, now let us see for the, if you see, look at the graph. If you look to the graph is a straight line that pass through the origin. And every time, if you want to calculate, right, the slope of the graph, this remain, yeah, this stays constant, as you see. Look, for example, See here, if I just want to do it within this portion, see here, for the graph like this. So you see, look, that how is it happening, the change in length. Look, for the force of what, for the force of 4 Newton, you see, look, you have this change is what, that it is to the 8 centimeter. So if you see, look, for the change in force, so what is that force on the y, this is, for example, look, our x, sorry, see here, our x1, look at this point, x1 and y1, what is this, x1 y1, let this is to be, as you see from the origin, it is 0 and 0, and when you increase the force y2, then this is your x2, and if you calculate the slope as the slope of the graph, which is equal to what, y2 minus y1 and x2 minus x1. So that is what is y2. It is the y2 is the 4. Okay, the it is equal to 4, and that is the 4. And here the length is what? The length the 4, and y1 is what? Y1 is 0. It is what? It is 0. Y2 minus y1, right? Before y1 is 0. Now what is your extension? That is what? That is 8. And what is it? That is 4. That is the x1 is, sorry, the x1 is 0, right? So what happens here, this comes out to be what, this comes out to be 4 by 8, so this is 1 over what, 1 over 2. So that is the slope of what, that is the slope of the graph, right? And here you see that, look, what does this actually mean, that the that is that this every time when you calculate this within the elastic limit, then every time it comes out to be what, it comes out to be the same number, and that would be what, that would be, look, if you just see, this is the Newton, and this is what, this is in meter, and we will be having what, 0.5 Newton meter. So the slope of the graph here gives you what, the slope of this graph gives you a constant called the spring constant. We call it what, we call it the spring constant, right? And that spring constant, which is force acting per unit length of an object. So the force that acts per unit length of an object, that is called the spring constant. And this spring constant depends on the stiffness of the spring. Okay, it depends on what, it depends on the stiffness of the spring, and further the stiffness of the spring depends the nature of the material, the uh, thickness of the material or the wire from which the spring is made, and the that is, and the diameter of the wire also. So it depends on those many factors, right? So that is what gives you the spring constant. Clear? Now let us that is, look, remember that it is the force extension graph. Okay, the force extension graph, right? Now let us see that the beside this force extension graph, there is what, there is the stress to strain graph, right, which we want to show. That was I did for the spring. So here you see that, look, we have what, that we have the force and extension graph right over here for the, that is actually the stress, right? In fact, the force to stress graph I explained, the stress to strain graph, right? Now you see that within the elastic limit, the ratio of stress to strain remain constant, or strain is directly proportional to stress. So here you see, look at this point, that this point is called what? This point is called the elastic limit. It is called what? It is called the elastic limit, right? Now you see in this case that look here, this is what? This is the region which I call the hook region. Whose region? This region. It is called the hook region. Why it is called the hook region? Because the hook law is obeyed here. This is known as the hook region. The hook region, or that is the that is the, here within this portion, here the body is in what? The extension is directly proportional to what? To the stress applied. The hook region, or we can say that this is the uh, elastic region also, or elasticity portion. Elasticity, this is elasticity, right? And beyond this, once you cross the elastic limit, then what happens? If the material is not ductile, means that which cannot be stretched or which cannot be drawn into sheet, then definitely what will happen right here, that this region, it will like what? Like this. And this is what I can call the plasticity. This region is what? The plasticity. The body, there occurs what? Permanent deformation. The deformation here is what? Deformation. It is permanent. Permanent deformation. The body is unable to come back to its original position here. That is what? That is permanent deformation in the body, right? And this region is called the plasticity. And beyond which, when you further apply the stress, when you increase the stress even more, then what happens? That there arrive a points which we call the breaking point. The breaking point. If you increase the stress further, then what happens? The object or the given substance break. Okay, so this is the elasticity region of the graph where the Hooke law is obeyed. This is the region where the stress is directly proportional, the strain is directly proportional to strain, but within what? Within the elastic limit, right? Once you cross the elastic limit, then there occurs permanent deformation. Even if you remove the stress, the body will be unable to regain its original shape and size again. So that will, there will occur what? There will occur permanent deformation. And when you increase even the force even more, then there will be a point arrived which we call what? Which we call the breaking point, and the body will break at this point. So this is all about what? And this is all about the Hooke law. Now there is the another topic, most probably the last topic of the uh, this chapter, and this is the young modulus. Young, the young modulus. As I told you that The Hooke law, in the case of the Hooke law, this constant varies they in the sense or in the way that whether the strain is longitudinal or tensile, whether the strain is shear strain. By shear strain means area, change in area related to area, or whether the strain is what? Whether the strain is volumetric. So now what is the Young modulus? The Young modulus tells us that the ratio of stress to strain always within the elastic limit, within the elastic limit, within the elastic limit, within the elastic limit, the ratio of stress to strain always remain constant, always remain constant. That is, mathematically we can write that Young modulus, this Young modulus equals the Young modulus Y equals stress by strain. Which strain? Tensile strain. Strain, that is strain, tensile strain. Okay, because if you change the strain to volumetric, then it will be no more a Young modulus, it will be a bulk modulus. Okay, so the Young modulus equals the ratio of stress to strain. And now I'm coming to that point, but let me demonstrate this to you. Let us see that, for example, if we have an object is C, let us see this object, a cylindrical shape object, right, as I did here. You see, this is what? This is the original length of the object called L naught, right? And this is the area of cross section of the object. This is area, right? And this area, I mark it as A. This is area A. This is area A. Now, there are two situations. The rod which has length L naught can either be stretched or compressed. So let us do stretching. So if you apply a force, let the applied force be this F, right, on this side, and let's say this F force on this side, on the area. So what happens to the object? The object will stretch, and I will show the stretching instead of one, I will show it in on both the sides. Now let us see what happens. The object will now stretch as like this. Its length increases and the volume will decrease. Remember, it cannot happen that your length increase and nothing will happen to your area. Why? Because if you just look to the volume of the cylinder, what is the volume of the cylinder? A into H, right? And the volume of the cylinder remain constant. So if you increase A, H decreases. The H, better to write the length, okay? Here, the length will decrease. right? And if you increase length, the area or the thickness will decrease, right? So under the action of the force which we have applied on this rod, so under the action of this stress, because you know that, look, what is stress? This stress is equal to force per unit area on both the sides. So you have the force and you have the area. Now look, when you, that is when it is under stress, then what happens? This is area, this is area. The new length of the object become what? This is the final length or the new length of an object. Let this be LF, or the final length, or you can say L dash, or just simply you can say L, whatever you like. And the force is still under the action of the stress. There is still stress, okay? But this all will happen in the elastic limit. Now let's see that what is the change in length of the object. It is elongated by this amount, by delta L, right? So now when it is compressed, then it will be decreased by this delta L, okay? And what will happen to, look, this delta L will equal what? Final length minus the initial or the original length, right? So if it is stretching, this will come out to be positive, and if it is compression, then definitely it will come out to be negative, right? So that is what then the by the definition of stress to strain, as you know, stress is force per unit area, and what is strain? Strain is the ratio of change in length to the original length, the change in length to the original length L naught. So our equation will become that y equals, what is stress? Force per unit area. And what is strain? This is delta L by L naught, or more simply we can write it as F into L naught into A delta L, or this will come out to be F L naught A delta L, where Y is called the Young modulus, and the SI unit of this Young modulus is, its SI unit is what? SI unit. The SI unit of this Young modulus is Newton per meter square, right? It is different for different material, depends on the nature of the material, on the nature of the material, and is different for different material, right? You can see your book for reference, like for iron, for steel, and for almost any substance you can see on the Google, and for few substances are you can refer to your book, okay? So you may have this thing there, okay? That is, the question is that what does it determines? It determines the strength of the material. It determines the strength of what? The strength of the material greater the Young modulus, then the body, yeah, the object has greater ability to withstand heavy stress or forces, right? So I have forgotten, unfortunately, in my previous lecture to tell you about some applications of the stress also, that where we can use the stress, right? So stress has merits and demerits. For example, we can use stress for cool cutting. Cool cutting is cutting without heating object. For example, even you can use the beam of the water, the high pressure beam of the water, to cut objects, right? That is, you can use mm, very high stress to cut thick sheets of steels and iron rod, right? You can use this to crush hard material also. So stress has a lot of application. And the Young modulus, this actually determines the strength of the material. And usually uh, before using those material, their strength is determined first, that how much pressure it can withstand. For example, one which I remember is about steel and tungsten. The steel has around 200 Newton per 200 into 10 raised to the power uh, something like 8 or like this. I don't remember by heart, but the 200 figure I remember. And for the tungsten is the highest, that is 400, and into 10 raised to the power, of the order of 10 raised to the power 8, I think, or 6. So tungsten has the greatest young modulus than the steel. So this is why tungsten is more mm, uh, has more strength than the steel, right? So that is the yeah, that is all about the young modulus of the given material. Now, if you know the young modulus of the material, then you can determine the change in the length of an object due to stress. And this will be equal to F naught into A and Y. Or even if you know the stress, then directly you can write that stress into the original length of an object and the young modulus of the object, right? So that is the expression. If the change in length is required, you will see some numerical in your book, where either will be asked for the young modulus to find by giving these things, or either you will be asked for the change in length, or if they want the final length under stress. So what will happen? This is LF minus L naught into F L naught AY. You can even make your own expression for simplification. So LF, the final length, will become equal L naught into F L naught into AY, or this will just be simple like this, that L naught into 1 plus uh, force per unit area, this one into young modulus, or more easily L naught into 1 plus stress into the young modulus of the given material for the tensile strength. So this equation can be used to calculate what? To calculate the final length under stress. So today you have learned about the Hooke law and about the Young modulus. The Hooke law describes you the relation between stress and strain, or Hooke law simply tells you that the force extension relationship, right? That that is the extension. F is directly proportional to the extension. Greater is your extension, greater will be the force required. Or F equals to kx, where k is the constant of proportionality, and it will be equal to like F by X, where for the spring, this K is called the spring constant, and this is unit Newton per meter, and it determines the it depends on the stiffness of what, on the stiffness of the spring. That greater the stiffness, greater will be the value of K. So what does this means? For example, look that X equals F by K, like that. Okay, now what does this means? That the greater the stiffness, there will be what, there will be very small change in the length of an object for the same applied force. Okay, so that is the Hooke law. The Hooke law for the certain kind of material, usually ductile material, the Hooke law can be represented graphically by this way. Okay, here the Hooke law tells you that strain is directly proportional to stress within the elastic limit. You see here, this is the elastic limit. Once you cross the elastic limit, there is no linear proportionality between stress and strain, and that is the curve vary from its original relationship, right? And the body, there occurs permanent deformation in the body, and we call that plasticity. So even if you remove the deforming force, the body is unable to come back to its original position, or the body is unable to regain its original shape and size. And if you increase the stress even more, then there arrives the breaking point. Okay, and the body breaks. Clear? So that is all about what? That is all about the Hooke law. So this is our today lecture, right? So thank you very much for being here. And if you have any queries and any question, you can ask me on Zoom or on WhatsApp. So thank you very much. See you in the next lecture.